Assalamualaikum and a very good day I bid to Dr. Haikal. So we are from group 7. So in today's presentation, we are going to explain on gas solubility in liquids. Before we start, I would like to introduce our group members. So there are 5 members in our group. I am Nurin Afrina Izzati binti Muhammad Razaid, metric number 198456.
My name is Nuriana Akila, matrix number 199043.
My name is Pavitra Jayakumar with matrix number 197581.
My name is Muhammad Irfan. My metric number is 198435.
My name is Luining. My metric number is 200468. Before we starting our presentation, so let's make some cheers for our team spirits.
Yay!
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 We love you, PM!
We love chemical engineering thermodynamics.
We love Dr. Haikal.
Yay!
Yay!
Okay.
So now, let me start the presentation by first introducing the contents of our presentation today. So firstly, it will be introduction, followed by Henry's law, effect of temperature, example question, and finally conclusion. So I will now introduce our topic. So first of all, solubility of gas in liquids has been a subject of great practical and theoretical importance since the start of modern science. So many industrial processes require knowledge of gas solubility. This includes synthesis of compounds, flotation of ores, steel production, manufacture of plastics, carbonated beverages, glass manufacture, and fertilizers. Therefore, in this presentation, we are going to introduce the concept of gas solubility in liquids. Basically, gas solubility in liquids involves the concept of gas dissolving in a solvent. Solubility of gas in liquid depends on temperature, partial pressure of the gas over the liquid, the nature of the liquid, and the nature of the gas. So, a number of quantities are in use to express the solubility of gas in liquids. Some of them are mole fraction at standard pressure, Oswald coefficient, and Henry's law constant. In this presentation, we will consider using Henry's law to quantify the solubility of gases in solvents. When solving problems involving gas solubility, Henry's law reference state is commonly used for species when the system temperature is well above the species critical temperature. So, before we continue, I'm sure that all of us are already have a rough idea on what gas solubility is. Is it?
Yes.
Yes.
So now let me pass the presentation to Liana to give further explanation on Henry's law.
Okay, thank you, Nurin, for the wonderful introduction on the topic. Okay, so now I would like to proceed for the second part, which is the Henry's law. Okay, next. So basically, what is Henry's law? It is a gas law that describes the dissolved gas amount in a liquid that is proportional to its partial pressure of the liquid. And it shows the liquid viscosity, and it is typical to use Henry's law reference state where the temperature of system is above the critical temperature. And it's commonly the dissolved oxygen gas is considered as the solute, meanwhile the water is the solvent. And Henry's law constant value and data can be get at different gases in water, typically at 25 degrees Celsius. And the constant value also depends on the solvent and also the solid characteristic. And finally, the common Henry's law constant values are often used at condition of 25 degrees Celsius and at 1 bar pressure. Okay, next. So now I would like to derive on the Henry's law derivation. So as you can see at the top part of the equation, this is the typical Henry's law equation. So we are substituting the A and B in the equation, and we will add both of the equation, and we will get the equation at the middle, and finally we will obtain the final equation at the right side of the slide by substituting the equations. Okay, so next part, I will proceed with the Henry's law constant. Okay, so as you can see, both the table shows the Henry's law constant for various gases in water at 25 degrees Celsius, and also for the different liquids at 25 degrees Celsius also. Okay, so that's all. I think I hope that my explanation is enough. So are you guys understand with what I have explained on the Henry's law constant derivation?
Yes,
Very
Liana.
clear explanation.
Okay, thank you. So that's all for my part. I would like to pass the floor to the next part, Irfan, for the explaining the effect of temperature on solubility of gases. Thank you.
Thank you, Lena, for explaining this law. Now I will continue the presentation with the effect of temperature on solubility of gases. Okay. So generally, when we are talking about solubility of molecule of gases, we are talking about the attractive interaction forces between the molecules. So for solubility of gases, they usually has zero attractive forces between the molecules of gases. Okay, so when we dissolve a gas or any type of gas into a liquid solution, or we call the liquid as a solvent, the interaction between molecules of the gases and the molecules of the solvents will create the interactive forces. So that means there is the what we call as the solubility. Okay, so as we can see in the graph on the slide, as the temperature increases, the solubility of gases in the liquids will decrease. So how can this happen? So let me tell you, when we add the temperature or heat the solution, the heating will eventually give an thermal energy to the reaction to the attractive forces between the gases and solvent molecules, and that will causes the solubility of the gases to reduce. And that's why when we heat up the solution containing gases and liquids, the solubility of gases will eventually reduces as the temperature increases. Are you guys understand what I am talking about?
Yes, Irfan.
Yes.
That's good. So let's proceed to the next part, which I will pass to Yeni.
All right, so thank you, Irfan. So now we are going to move on to the session 4, which is example questions. Next slide, please. So, all right, so the example I will present is about the Henry's law problem at high temperature. Next slide. All right, so for these questions, we need to determine the solubility of the nitrogen gas in H2O at the 300 bar and 25 degrees Celsius, and we take the specific volume of the nitrogen gas equals to the 3.3 times 10 to the power of -5 meter cube per mole. All right, so next slide. Right, so in order to solve these questions, we need to assume the solubility is small enough that the liquid solutions remains ideal, and solving the mole fractions of the N2 will give these first equations, which is the X equals to Y times the fugacity times the pressure, then divided by the H, all right? So at the 25 degrees Celsius, the vapor pressure of the water is really small. So we need to assume the Y of the nitrogen gas equals to 1. Next slide. Okay, to find the Henry's law constant, we must correct the value for the pressure first. Okay, so we assuming that the partial molar volume at the infinite value does not change with the pressure, which means that we will get these equations. Then after that, we need to plug in the numbers that we get from the previous slide, and we substitute to the fourth equations. Then we'll get the answer 130,106 bar. Because of the Henry constant has increased by approximately 50% at the higher temperature, we need to finalize to solve for the fugacity coefficients. We need to assume that the Levis fugacity rule and apply the generalized correlations and use the values given in Appendix C from the textbook. And the reduced pressure and temperatures are as the equations 5. And as you know, the reduced pressure equals to the P divided by the PC, which is the critical pressure. Then we substitute the values we get from the appendix. Then we'll get for the PR equals to 8.88 and the reduced temperature equals to 2.36. All right. So by looking up the eccentric factor from the appendix A.1 from the textbook again, you'll notice that the W equals to 0.039. Okay. So that we can, using the value above again, and then we'll substitute into the 7 equations, and then we'll get the answer equals to 0.021, or the viscosity of the nitrogen gas equals to 1.05. All right, next slide. So for the final step, we need to plug in the values from the previous 2 equations, the last 2 equations, and we'll get these equations. Then we substitute the x of the N2 equals to 5 times the viscosity times the P, then divided by the H. Then we substitute the value we get just now. Then the answer will become 0.00242. So all right, that's all from me. So do I convey my informations in a clear way? Do you have need any clarifications?
It's very clear.
No, Yining, very clear. Very good job.
All right.
That's it.
So thank you.
Yeah.
So now I will pass to the Pavitra to give her for her last part.
Sure. Next one. Okay. Thank you so much, Yining, for the beautiful explanation. So now I will proceed the last part, which is the conclusion. Next slide. So for the conclusion, in order to occur the solubility of gas in liquid, it totally depends on 4 methods, which is the first one is the nature of the substance, which is also known as solute. The second one is the nature of solvent, temperature of the solution, and pressure. However, temperature of the solution and pressure is the greatest influence in order the solubility to occur in a liquid. So in short, for the temperature, the solubility of gas will decrease if the temperature increases. This is because gas dissolves in a liquid with evolution of heat, like exothermic process. This is according to the Le Chatelier's principle. The same goes to the pressure as well, where the solubility of gas increases if the pressure increases. This is because concentration of the dissolved gas is proportional to the pressure on the gas above the solution. For the gases such as hydrogen, nitrogen, oxygen, and helium, it dissolves in water only to a small extent. However, the 3 gases which are ammonia, sulfur dioxide, and hydrogen chloride is very highly soluble in water. This is because most soluble gases are those which chemically react with the liquid solvent. So this is our part for the conclusion. Do you understand?
Yes. Thank you, Parivita.
All right, thank you so much. This is the end of the presentation.
Okay, and lastly, I would like to thank you. Lastly, we would like to thank you, Dr. Haikal, for all the guidance and helps that enable us to do this presentation throughout our course in chemical engineering. Yeah, without you, we cannot do this presentation and also proceed with our course. So and again, thank you, Dr. Haikal, and we love you.